This is where we left off, saying that half-life time is the time it takes for the radioactivity of something radioactive to reduce to half of its original level. And the way we find the half-life time from a graph of activity versus time is to look and see where the curve cuts the activity axis, halve that number, go across at that halved number, and at the point where that horizontal line hits the downwards curve, drop a vertical line down to the time axis and read off the number there. Let's say that Sassy Sarah's boyfriend, Dodgy Bob, comes home with a lump of radioactive waste as a romantic present. After she has told him that flowers or even an Arbroath Smoky would have been nicer, she sensibly decides that it would be interesting to find the half-life time of this unappreciated gift. So how does she do this? We know that she will need to get a graph of activity versus time, so she will need to take activity readings with a Geiger counter at regular time intervals. She will need to plot these points, put a curved line of best fit through them. By the way, why do people have this silly idea that lines of best fit must be straight? And must be through the origin? This one will be neither straight nor through the origin. And she will plot the points as neat little crosses, not horrible blobs. After all that, she will use the graph to find the half-life time, in the way we have just described. So, Sassy Sarah pulls out her Geiger counter and a stopwatch, takes the initial radioactivity reading at 0 time, then starts the stopwatch, taking readings every 30 seconds, maybe. She soon ends up with a long table of activity readings at these regular time intervals. However, can you spot an issue with what the Geiger counter is actually picking up? There isn't just the radiation from the radioactive waste that's hitting the Geiger counter, there is also background radiation hitting the Geiger counter too, which is giving us an artificially high reading. We only wanted the reading for just the radioactive waste on its own. So what can Sarah do? Fortunately, like the shipwrecked mariner, Sarah is a person of infinite resource and sagacity. You see, before she pointed the Geiger counter at the radioactive waste, she measured just the background radioactivity in the room itself. Now this gives us a way of finding only the radioactivity of the radioactive waste on its own. We simply subtract the background reading from our measured results. Now Sarah has what we call corrected activity readings at regular time intervals. An activity versus time graph can be drawn, and from that, the half-life time found, in the same way that we did before, halving the starting activity on the activity axis, reading across at that halved value, and then down. Knowing the half-life time of a radioactive material lets us then accurately know how radioactive that material will be in any chosen amount of time in the future. During the Cold War, government physicists used this process to work out how long people would need to stay inside their houses for, following a nuclear bomb, so that they were no longer going to die of radiation sickness from the waste all around them. Remember, all radioactivity gets less over time. Anyway, in this example, a radioactive material has a starting activity of 120 becquerels, and we need to calculate what the activity will be 30 days later, if the half-life time is 10 days. Firstly, we need to find out how many half-lives are in this big lot of time. So if the big lot of time is 30 days, then that's 30 days divided by 10 days, which is 3. So that's 3 half-lives. So that's 3 times we have to halve the starting activity to get to what will be the final reading. Here, a radioactive material has a half-life time of 5 hours and a starting activity of 1000 becquerels, and we want to know what the activity will be after 10 hours. We first need to find how many half-lives are in that big lot of time. So we get that big lot of time and divide it by the half-life time. So that's 10 hours divided by 5 hours, which is 2 half-lives. Then we take the starting activity and half that number twice, to end up at 250 becquerels. A slight variation on these questions is when they ask you what the activity was at some time in the past. But the thing is, in the past the radioactivity would have been greater. So if we are asked to go back in time, we multiply by 2, a certain number of times, not divide. In this question, the current activity is 8 becquerels, and given a half-life time of 10 minutes, we want to find what the activity was an hour ago. In just the same way as we started the previous questions, we work out that there are 6 half-lives in this big lot of time. So, because we are traveling back in time, we multiply the activity value now by 2, 6 times. Eventually we end up with 512 becquerels. It's worth saying, if you have a long chain like this one, it's a good idea to double-check that you've done the right number of doubling or halving, because it can be easy to do one too few. Here's the final half-life example, and it's another very slight variation. If a radioactive source decays from 80 becquerels to 20 becquerels in 60 minutes, calculate the half-life time. This time, it's the radioactivity at the start and at the end that we know most about. So we start with the starting number and keep halving that starting number until we get to the finishing number. The number of times we have done this halving process is the number of half-lifetimes that have happened. Then it's just sort of numeracy, saying, well, if 2 half-lifetimes are 60 minutes, then 1 half-lifetime is 60 minutes divided by 2. So the half-life comes out to be 30 minutes. Story time now, so relax. Way back in the 1950s, when Queen Elizabeth II came to the throne, the old post boxes across the UK were replaced with ones with an Elizabeth II mark on them. But the Scots didn't like this, because the original Queen Elizabeth, the one during the Spanish Armada, had never been Queen of Scotland. These post boxes saying that this was the second time an English Elizabeth had ruled Scotland were wrong, and had to go. So somebody did what any rational person would do in this situation, and started blowing up post boxes. Their cunning plan was this: as a result of one post box being blown up in a particular area, some people would be inspired to blow up 3 more. Each of these 3 blown-up post boxes would inspire another 3 post boxes to be blown up. Each of these 3 blown-up post boxes would inspire another 3 post boxes to be blown up. And so on, and so on. So 1 blown up would lead to 3 blown up, would lead to 9 blown up, would lead to 27 blown up, would lead to 81 blown up, would lead to 243 blown up, would lead to 729 blown up, would lead to 2,187 blown up, would lead to 6,561 blown up, and in a very short time, these terrible new post boxes would be gone. Of course, it didn't quite work out like that, and we still have post boxes. The nuclear equivalent of blowing up a post box is called fission. What happens with fission is that a neutron is fired into a nucleus. The nucleus splits right in half, there's an almighty release of energy, and 3 more neutrons fly out. Now, whilst any old post box can be blown up, there are only a very small range of atoms that can be split, or blown up like this, again, what we properly call fission. Because this special kind of blowing up releases 3 neutrons, we can make sure each of those neutrons goes on to fission 3 more atoms. Each of those new 3 neutrons will go on to fission 3 more. And each of those 3 will go on to fission 3 more. The pattern of blowing up energy release is 1, 3, 9, 27, 81, 243, 729, 2,187, 6,561. But every single individual split released loads of energy. So with those numbers, a pretty much unimaginable amount of energy gets released. This self-amplifying sequence is called a chain reaction. If we just let it happen, then this is an atomic bomb. But if we pull out a good number of these neutrons as they are created, then things are much more controlled, and we get a nice, steady output of heat energy. And this setup is called a nuclear reactor. The heat from nuclear reactors can be used to make steam, to spin a propeller for aircraft carriers and submarines, or it can be used to spin a power station generator, to make electricity. The good things about nuclear power stations is that absolutely heaps of energy is released, and then also, because they don't set fire to fossil fuels, carbon dioxide isn't given out. The disadvantage is that a small amount of radioactive waste is made, which people are disproportionately scared about, but bury it way below ground and it doesn't harm anyone.